Morning. We start our lecture on fundamentals of material science. Please write me if you have problems in hearing my voice. Otherwise, we carry on. We were talking about ideal material. The ideal material, as you may remember, is elastic up to failure. So there is proportionality between the stress and the strain. So the force divided by the section and the deformation you get on the material. It is homogeneous, so yes, it has no voids, no holes. It has the same density across the section. And so you can imagine that a composite material, a hybrid material, is not homogeneous. So it's not ideal. And then it is isotropic. That means that you have the same properties on the three direction across the whole volume. And having said that, you may remember as well that the ideal material, of course, is not existing, but it is a useful model to start thinking of materials behavior. There are some materials which are closer to the ideal and other which are less close. So they have differences from this kind of behavior, which is the which we assume it is the easiest to study. In particular, we talk about metals, because metals, which are materials which don't exist in nature, metals are the first materials which were developed by humans, which were extracted from rocks. In nature, you find metal oxides, but you don't find metals as such. Metals have the characteristic of having a particular metallic bond, which allows an easy mobility of electrons. Basically, you have cations which are, in a sense, immersed in a sea of electrons. Electrons are free to move, across the material, and cations tend to be steady. So in practice, it is very easy by this way to explain why metals are good conductors of electricity in the first place, but of heat as well. And on the other side, it is not easy to explain why, in which way you can have a behavior different from the elastic one. You cannot imagine how you carry on in having a deformation, a plastic deformation, because you can imagine that crystal metals are also crystalline, so they, in most cases, they have a structure which is ordered structure formed by kernels. We call kernels these I would say parts, nodes formed by cations and immersed in a sea of electrons. Electrons are put together, put in common between the different cations. We are not able to say which electron belongs to which cation. So kernels explain very well why the elastic behavior is prevalent. Although they don't explain much the fact that the material can have plastic deformation. It doesn't explain much why they can be, in some cases, even not always homogeneous. So in general terms, why they are not completely ideal. Although we can say that the material which is closest, the alloy which is closest to an ideal behavior is steel. So reversing the problem, material science became an ordered corpus or whole of elements when steel came into use. So at the end of the 18th century, basically. And it was started developing this kind of considerations on ideal material and on steel, which was close to the ideal, but on the other side, it had some deviation from ideality, which are important as well. We define the crystalline structure as a lattice, and that lattice, in general terms, is ordered. Then we need to explain, as I was saying, how in some cases, after a the application of a certain force, so beyond the elastic limit, we have some plastic deformation. This can be explained by thinking of the fact that we have defects. We have defects into our lattice, and the defects are important because they are able to explain the plasticity, and they are able to explain also the modification we can have to the structure of the metals, which allow them to be worked. Worked means that I can melt the metal and make objects, make structures out of it, or may join the metals, because, for example, I can weld two pieces of metal together, and this is possible because there are some defects and therefore some modification from the order of the lattice. Defects can be due to some simple events. One cation may be missing into the lattice. This is called the vacancy. Or I can have more cations than the one included in the lattice, because you need to remember that alloys are not formed by one single metal, but they are formed by one metal and some other metals or some other ceramics, for example. In the case of steel, I have iron and I have carbon. A limited amount of carbon, because in steel we don't exceed, the carbon is a ceramic. The cations of carbon are smaller than the ones from iron, and so they can, for example, replace one cation or go in between a few of them. So they may come into an interstice, or they may substitute one of the elements of the cation. This is not the only case, because then I can have steel which is formed by iron, but including not only carbon, but also chromium or nickel. And in this case, I may have cations which are smaller, but which are also larger. This explains the fact this explains the fact that I have internal stresses, not just the stress which is applied from outside as a force, and then it moves the kernel and then the crystal as a whole, all together. But there are also internal stresses, some part of the kernels which move with respect to some other parts. And that explains, of course, plastic deformation. But alloying is necessary in metals. I need to complicate a bit further that question in the sense that we could assume that a material without defect would be the perfect one. This is not the case. There are useful defects because, as I was saying, plastic deformation is also useful because it allows the workability of the material. But an idea which is important in material science, which has always gone through for a number of decades, I would say, because there is this always this concept that something without defect is perfect. So, of course, something without defects needs to be very small. And in fact, there has been quite a lot of research in trying to develop the so-called whiskers. Whiskers are hairs from cats in the normal language. And whiskers are also known in metals. There are elongated structures which basically have no defects. Whiskers have been developed in a number of metals, and they are very close to the ideal. They have been developed in tin, that's the image I'm showing here to the left, zinc, cadmium, silver, and so on. But of course, they have no defects and they are brittle. You can imagine that they are brittle. They are elastic till the end of their force application, so till fracture, and they are brittle. So they break very quickly and abruptly without giving any indication. On the other side, it's good to have a material without defects because there are some applications in which this is needed. For example, as a reinforcement for metals, in heat exchangers, in turbines, in the catalysts. If they have no defects, they produce an effective action, which we know perfectly what it is. In other senses, there are also bad whiskers. Whiskers are investigated a lot in plating, in electroplating. Electroplating is very diffuse because we apply a coverage to some metal or even to some plastic structure in order to make them conductive. This is one possibility, or to protect them. Zinc covering, it's typical zinc electroplating. What happens in zinc electroplating is that after a while you have some nodules. You have some nodules, some part of the structure which form some smaller bubbles, I would say, above the structure, which in the end they develop also whiskers. They tend to self-grow over the structure by the application of a force, because there is always a force applied to the electroplating, because remember that the plating, the coverage, doesn't deform at the same speed and with the same characteristics that what is below, what the main material, the bulk of the material. What happens is that in practice, some whiskers develop which represent a problem. Nature knows a lot about whiskers because whiskers are used in nature for basically your cat. If you have a cat, you may know that it uses whisker to fill a number of to have a number of indications, which may not translate directly into numbers, and so, but it feels vibration, displacement, and so on by the use of its whiskers. You may see that as always in nature, the whiskers have an obvious spiral structures, and also they tend not to have a constant section, and they tend to be made into progressing sections to the tip because they develop, they grow. This is the case for cats. This is the case for crickets. Crickets have been studied a lot because they have these cerci, which are basically the antennae of the crickets, and cerci allow crickets to feel, to have indications, to know about vibrations, to know about displacements, to know about the presence of noxious or good chemicals, because every one of us and also animals are able to, if they have, if we have conditions which are in the right pH range and in absence or in presence of some chemicals. So this is the case also for crickets, and there are a number of sensors. This is the surface of crickets, which have the surface of a cerci of a cricket, and of a circus of a cricket, and you can see some conical sensors which have a form of a cone and are chemical sensors, and you have some campaniform sensors. One is represented at a larger scale here, which allow crickets to know about displacement, to have indications about displacement. And whiskers, the proper whiskers, the filibriform sensors, are vibration sensors. Since we have we are always in need for vibration sensors and also other kinds of sensors, but our sensors may be quite ineffective in some senses. Then we studied a lot this kind of applications, the possibility of application of biomimicked to mimic the sensors which are present in animals like crickets to our needs. So to industrialize something which is mimicked from nature. There are other possibilities as well. You may know that, well, whiskers are in nature are of course not made of metal, because nature doesn't use metal as such, but they are made of proteins, of keratin. Keratin is a protein which is built from amino acids and as an hierarchized structure that you are able to build, nature is able to build some structures. It is important that keratin is becoming also an important waste, because some food-related industries produces a lot of waste into keratin. Not only food-related industry, because thinking of cutting hair, we produce a lot of keratin waste. Even a bit nasty as a kind of waste, but in some cases you need to reuse them. And this is going to come in terms of sustainability and circular economy. This is going to come more and more. Top left, you see the keratin feathers from sorry, whiskers from cats. Bottom left, you see the feather keratin from poultry feathers, from poultry feathers, which are a waste from food producing industry, from the breeding of breeding of poultry. And poultry feathers have been inserted as such either in plastics or in a smaller form, in a closer to the real keratin molecule form, in nanocomposites, to form nanocomposites. Because it is an abundant waste, because it is a waste which is biodegradable, and it is very strong in terms of tensile properties and so on. This is an example of what we can do with keratin, for example. I am trying always to make the comparison between what we do in engineering terms and what the nature does, and we try to apply to our engineering. Remember that materials in nature are always nanomaterials because they are hierarchized, and therefore we start always from the nano dimension and build everything up to a macro by a different number of steps and stages and levels. Okay, so basically you may have seen that smaller defects are formed into the kernel, but also larger defects are formed because the crystal is made of nuclei. And basically, once you, in practical terms, you form a metal, this is molten into a mold. It's molten into a mold, and in practice, what happens is that not the whole of the metal is solidified at the same moment, but it takes some time. For plastics, it's worse because for plastics, you don't have a precise temperature of solidification, as it is the case also for melting. You have an interval. For metals, since they are crystal, we have a precise temperature of solidification. But on the other side, they don't solidify all at the same time. It takes some time, and some nuclei are formed, and they are formed with their own geometry, and therefore they clash. They may clash different nuclei into the whole of the crystalline metal. And so you have grains, you have metal grains, and you have boundaries. You have boundaries between them. Therefore, one of the important characteristic in metals is to try to measure the grain size, try to measure the grain size, so they form grains which clash between them. They have some boundaries, and you need to understand how they clash, and therefore their relative dimension and their geometry. Because ideally you may assume that they are all spherical. This is seldom the case. They are not spherical because they tend to cover the whole of the space, and also they try to adapt to each other. But in general terms, it is important to measure the distribution of grain size into metals and to see which is the relation of distribution of grain size and workability, and the way to work them, the way to manage them in order to make pieces and structures and so on. This is not easy because there is a kind of, it's not a Gaussian curve you have some complex distribution of grain size. Also, there is another problem because they are not spherical. So you should assume an equivalent diameter to adapt as far as possible their shape to a kind of equivalent dimension, supposing they were sphere. In some cases, as you can see with copper, bottom left, they are far from spherical. They might be needle-like. They might be closer to needle to cones and so on. And you may imagine that this is quite tends to be difficult. This is another movement away from ideality, because ideality would say that we have just one crystal. That's all. Which happens on whiskers. Very small structure, you may have just one crystal width. It's not possible to not to have defects. You need to have one defect because otherwise the whisker wouldn't grow. For thermodynamical needs, you would need to have at least one defect. You will see it later on that you need to have one. But in this case, you have countless defects, and you need, in the real case, you need to adapt that fact to the idea that you have to use apples. Okay, carrying on. In some cases, you are also subject to the dimension of the mold. Of course, the mold is not infinite. You may consider it's like making a cake. You have a container in which you allow the cake to be prepared and put it in the oven, and then it develops in different ways depending on the distance of the wall of your container, your oven tray. And so this has consequences. In the case of the cake, the consequence may be that if you are close to the wall of the limits, boundaries of your oven tray, it may be burned, for example, because it's close to the oven tray, which is in iron or in aluminum or whatever. And in the case of metals, that the same thing happens in a sense, because there are some structures which develop and the solidification starts from the sidewall, from the limits, from the boundaries of the mold, which means that in the end you don't have only, you have the question of the different nuclei starting growing, starting crystallizing, but you have also some different structures which are dendrites which tend to solidify in some places from the metal. And it's interesting because dendrites are hierarchical structure, even if metal is a not natural material, it's a material which has been produced by humans. So in a sense, it is synthetic. It has been produced by humans. Then you have these dendrites, which on the other side show as hierarchical structures. And for this, in this sense, they are present also in natural materials like ceramics. There are ceramics which are natural materials like calcium carbonate, calcite, aragonite. You know that they come from nature. Of course, dendrites have some consequences, and they change the hardness and stiffness of the metal. Stiffness, you know, which is measured by Young's modulus. It's the ratio between stress and strain. Hardness, it's a local measurement. It's a local measurement. We will talk later on in this lecture a little bit more on hardness. We will give more effect, more indications. One thing it's important to say at this moment that hardness is a technological measurement. It's not a physical measurement, because hardness has got some scales which are not physical scales, but they are comparative scales, empirical scales. And that's important to know. That's the first thing to know. But hardness is important anyway because of workability of the material and of local properties. Hardness is the resistance to indentation. So the fact that I put a dent, I would like to create a dent, I would like to penetrate locally the material. Okay, they have consequences, the presence of dendrite, they have consequences on electrical conductivity, on welding, difficulty of weld materials or connect materials together. Welding is still the main possibility to connect materials. And therefore, it's important to evaluate if dendrites are present. There are a number of studies on that. I am saying all these things because as far as the course progresses, it's important that you make your mind, that you get curious about some elements, some of the things I'm saying, and possibly you try to go deeper into that and to see if you may build a project or you may investigate literature further. But of course, we are just at the beginning, so there is time to do that. Okay, so defects, big defects. So due to the fact that there are nuclei and there are grains and so on, nuclei form grains, grains collide between them, they clash. Therefore, there is a theory. There is a theory to try to understand, try to model how big defects move around. So basically, there are some defects which can be modelized into two main defects: edge defects and screw defects. Again, edge defects, edge dislocations. Dislocation means that there is something out of place and therefore there is plastic deformation. Something out of place may indicate boundaries between grains or may just indicate there is a vacancy or there is one cation more in here, interstitial cation and so on. Anything of this create a dislocation, so a movement, an unexpected movement, which might be an edge dislocation or a screw dislocation. So this unexpected movement may go in plane or may go out of plane. In plane means that you move basically by a shear stress. There is always a shear stress. I mean that it's perpendicular to the tensile, strength, to the tensile stress. So I have a shear stress, a shear, I would say it's a shear tensile in a sense. And there is a slipping plane. So there is a plane parallel to which you have a kind of sliding. Or you have a screw dislocation, and therefore you may have a kind of torsion, out of plane. You may have a movement. These are ideas because, of course, the real movement occurs partially in plane, partially out of plane. That's the common way of working. But this is useful as a model because it gives the idea of how plastic deformation occurs, and also it gives an idea of how the real deformation takes place. You may have an edge dislocation, so with an extra sheet of atoms, you may model with an extra sheet of atoms of cations in reality within the lattice, or you may have an hélice-like surface. So the plastic deformation may go either in plane or out of plane. That's the substance of the thing. And you may represent each deformation which is a combination of in-plane or out-of-plane, by a Burger's vector. A Burger's vector, which gives you an idea of how much of the component is in plane and how much is out of plane. This is useful not only in mechanical terms, but also in macro mechanical terms, because in the end you find out that you have a braking surface, you have a displacement surface which ends up with a fracture surface. So plastic deformation, we understood that plastic deformation leads to failure. Sooner or later it leads to failure. You may have little plastic deformation and therefore, or no plastic deformation at all, and therefore you have a fracture surface which is abrupt, which is clear, which is even in some cases it looks very smooth and so on because the failure was abrupt. But in general terms, this study on Berger's vectors allow you to understand which kind of failure you will have. You will have shear tips and so on, and which will allow the study on Berger's vectors will allow you to understand more or less the type of failure which you are going to expect, and make prediction also on the final plastic deformation you may have, and the possibility, and when the force is going to drop, when the stress is going to drop. Because before failure, with plastic deformation, at some time, the failure is going to drop at a certain point. Well before that, you need to stop using the material, well before that load drop. But doing predictions about when the load is going to drop, it's important anyway to use the materials. Without going into many details, you need also to consider that there are different shapes, different cells of the crystals. And basically the atoms can be disposed with lower, dense, less dense, or more dense packing. They can be heavily packed or less heavily packed. So if they are less heavily packed, the consequence is there is more space for some other atoms to go inside, to enter the crystal, to be clear and beautiful. In other cases, they are so heavily packed that there is not much space to include other atoms. This is important for alloying and so on, because of course alloying requires other mixing with other atoms and of other metals, of other ceramics. In other case, you may have carbon, but you may have also aluminium, for example, aluminum oxide, silicon oxide, and so on. The original iron was full also with silicon oxide, with silica, because they were extracted from the rocks, and silica was still there. It was difficult to get rid of silica. The temperature needed for that were very high. It wasn't the case at that. So lots of iron which was used in the 18th century and 19th century was of silica, which of course reduced tensile stress, but on the other side gave higher hardness, so it influenced the use you can make of iron. Okay, so there are basically three types of crystal lattice shapes, geometries, which is one is the body-centered cubic with 9 atoms per unit cell. So basically you have atoms on all vertices of the cube, and one that is the center of your cube, and the cell is cubic. You can have also another cubic cell but with not only atoms on the vertices, but also atoms on the center of every face. And since the cube has got 6 faces, you have 8 plus 6, 14. Then you have the hexagonal compact, which is the most compact one. You have basically the section which is hexagonal, and you have atoms also on all other vertices in this shape. And you have a mix of faces, which are some are squared and other are triangles. But the section is an hexagon. That's why it's called hexagonal compact. It's called compact because it's the most compact with respect to the other two. This applies to a number of metals, not just to iron. In iron, we are going to talk about iron A and iron alpha and iron gamma. Iron alpha is going to be called ferrite, and iron gamma is going to be called austenite. And this is a difference which we are going to discuss a little bit further on. Anyway, the question is that the crystal lattice, of course, the shape of the crystal lattice and the packing of the crystal lattice, the geometry influences the ability to create alloys, and which kind of metals you create alloys. You can imagine that iron gamma, it's happy to include nickel atoms, whilst iron gamma is happier to include chromium atoms. This is general and brutal and so on. Then there are other considerations because in practical terms, there are some situations which are hard to manage. For example, an alloy between iron and aluminum, in practice, it's very difficult to obtain. And possibly it's not even very useful because then there are differences of density. But in general terms, it is true that a similar structure, lattice structure, tends to include metals with the same structure, tends to be alloying with metals with the same lattice. Okay, having said that, we were talking about hardness. This is a kind of a hardness test. With respect to tensile tests, you can see that hardness tests, it's really very, it gives very basic information because we compare. Technological test means that we compare with something. We assume that something is 100 and we compare the hardness of our metal. It's a bit more complicated than this because we have hardness scales for every material. You may have Shore hardness for plastic, knop for ceramics, knop hardness. You may have Brinell. Brinell is the main one for metals, and you have Vickers as well. This is a test. This in reality, the image shows a Vickers test because you have a diamond tip which indents the material and produces a trace, an indentation of some dimension, which is measured, and it gives you an idea. The larger it is, of course, the softer the material is. If it produces a small indentation, the material is harder. This is obvious. Having said that, there is a correlation between hardness and the also the ultimate tensile stress, so the tensile stress at which the material breaks. Basically, there is this formula. I wouldn't use many formulas, don't be deceived, but I wouldn't use many formulas in my explanations because it's more important to focus on the problems, which in material science are countless, than to give formulas, because you can see that formula, for example, that formula, it works very well because it gives you an idea of, you apply a force, you press a force for 10 to 15 seconds, the standard says, against the metal. Then there are a number of requirements because you need to have, the metal needs to be completely flat, which is easy for many metals. For example, stainless steel, it is easy to have a flat surface. Other kind of hardness tests are more difficult because, for example, with plastics, having a completely flat surface sometimes is not that easy. Flat and thick, quite thick, because there is also a limit of that, because you cannot make a Brinell test of a half a millimeter sheet, because you will get the material penetrated by the tip, and this is not what you want. You want to create an indentation, but not to penetrate it. An indentation that keeps the material flat anyway, sort of flat. So a small indentation in comparison with the thickness of the material. So you can consider the material as a whole and say, well, it is flat, although it's an indentation. If the indentation is so large that it's so deep that it produces some inflection of the material, then you will have that problem of validity of the Brinell test. So this gives you an idea of what are the basic problems with hardness measurement. The main problem is that Brinell test doesn't give you a measurement, an objective measurement. It's also a comparative measurement against some other materials which are considered to be of, with a certain value. You may say that one material, one metal is 100 on the Brinell scale, and another one has a lower hardness. But you don't have, it's an empirical scale. What you have as for physical measurement is the force you apply in Newton and the diameter of the sphere. Then there is the big question to measure this small diameter of the indentation, which in some cases is small and it might not be completely circular. So you may need to do some kind of assumptions on the equivalent diameter and so on. Anyway, in terms of comparison between hardness and tensile stress, this is interesting because hardness measurement, also hardness tester, much cheaper than a tensile test. So you may not have or not be in the position of making a tensile test because you have to cut the samples, have no bones and so on. So you need to have the molds, etc. You may consider that a hardness test would do before trying to do some more evaluation as tensile tests and so on. And so there is a kind of proportionality, depending on the type of steel, between the ultimate tensile stress and the Brinell hardness. Of course, into an elastic behavior. We need to have an elastic behavior. If you have a steel which is too plastic, then you may have some problems. Anyway, carrying on with this kind of evaluation, you may remember our stress strain curve. Well, initially it was a line, then it becomes a curve when you start with necking, with plastic deformation, etc. This is very simple, very brutal, I would say. And you have basically a hard steel. You can see that the hard steel shows less plastic deformation, a higher Taylor stress in most cases, and a smaller plastic deformation. Soft steel, this is very general, because then we can say how hard is hard and how soft is soft. But if you compare two types of steel, one which is hardened and the other one which is softer, you may see that here you have a Young's modulus is about the same, so the slope it's about the same because the slope doesn't change much. Young's modulus doesn't change much into steel. But what changes is that hard steel has got just a little bit of plastic deformation that then it breaks. We could even think of neglecting the plastic deformation, saying there is no plastic deformation there. Of course, it's brittle. It's much more brittle hard steel than soft steel. Soft steel has a lower elastic limit, point B, but the stiffness is about the same, but for a lower elastic limit. So the elastic behavior stops before, and you have quite a large amount of elastic, plastic deformation. So it's more workable. Softer steel might be more workable because plastic deformation allows you to work the material. Because if you act, for example, turning steel, if you want to produce tubes, for example, you need some plastic deformation. And that might be usable. There is a problem in that, which is necking. There is apparent stress. If you assume, for example, that I'm saying, just to say a number, if you assume that your specimen is cylindrical and has got a 10 millimeter diameter, well, it's 10 millimeter diameter here. And for hard steel, you can say up till to the end, it's about 10 millimeter diameter. For soft steel, that doesn't work anymore because you have a lot of necking. You have a lot of necking. So at the beginning, it was 10 millimeter diameter. Then it becomes to be less and less and less. It might become 5 or 6 millimeter diameter. Even worse, it might have a section which is no longer circular. It may be deflected by some sort of shear stress and so on. So what happens in practice is that you have an apparent stress. The apparent stress means that if it was 10 millimeter diameter, I assume it's always 10 millimeters diameter. Apparent stress is not true. It's an engineering in the sense that, well, it is not physical, it's engineering. I have no money, I have no time to evaluate how much is the necking. I assume the apparent stress is that one. The actual stress, it's real. It's the real one, and it takes into account the necking. While the engineering stress, it's easier because actual stress, you are making an assumption that I need to measure the necking every time. Every single moment I need to measure which is a section of the sample. You can imagine it's not that easy. It's not that easy. In some cases, you just measure it at the end and you assume that it's changing gradually over the time, and from the time when plastic deformation starts. So taking into account the necking might be important. Otherwise, you tend to underestimate the real stress you are applying. And you may have a sudden breakage, which may be unexpected. You consider that the apparent stress is less. Okay, at a certain point you have failure, and in this case you may consider that it's much more workable because you are able to accommodate 25% of the formation. Here you are able to accommodate 4% of the formation. That makes a huge difference, because if you are mechanically working on the material, well, 25%, it's more than 5 times than the hard steel. Okay, having said that, I don't say much more than this. I would like to conclude with some observations, that we have basically three main characteristics to start with. We have stiffness, hardness, and toughness. So stiffness is the resistance to deformation. We measure stiffness with Young's modulus, and if the material is stiff, it has a low elastic deformation when a force is applied. Please remember that stiffness applies only to elastic part of your curve. So to come back to here, you are allowed to measure the Young's modulus up to here, up to the elastic limit. When it curves, when it starts curving, for example, for hard steel, it starts curving at 5,600 or something like that, megapascal, then you do your measurement of this slope, and this is the elastic limit. And the stiffness doesn't change much, as I was saying, between hard steel and soft steel. Usually we are in the region of 200 gigapascal of Young's modulus. The other question is that in some cases you will see some materials, well, with steel everything seems ideal and you may be happy about that. With other materials, the problem is that you don't have any part of the curve, of the stress strain curve, which is really aligned, which is really linear. You have some behavior which is a bit fuzzy. Plastic deformation starts at the very beginning with plastics. Plastics are called like that because plastic deformation starts at the very beginning. That's why we are not doing screws. We are hardly doing screws with, and especially springs. We are hardly ever doing springs with plastic. We do some springs with nylon, because with nylon we have, for small forces, we have a sort of elastic behavior. But doing a spring with plastic means that the spring will undergo plastic deformation very easily with very small forces. You will never see, I hope to be wrong, but you'll never see a polyethylene spring, because of course it would cost 1/10 of a steel spring, but you have no real elastic behavior. And we are going to talk a bit about plastics. You know, this course is not that long, so I try to do my best to cover all the materials and all the main characteristics. But anyway, what else? The other question is that you have hardness, which is connected with stiffness if you are in the elastic field, if you are talking about metals. In plastic is not, of course, the same question. Hardness is the resistance to penetration, and if the material is hard, it would not allow another material to penetrate. So you press the material. Hardness, please be aware, the material doesn't fall on the other material. You press against it for some time. Renal test says 10-15 seconds. Other types of tests say another amount of time, but it's always this kind of time. Is a very quick test. And then you produce an indentation that keeps the original material to be measured flat anyway. Otherwise, the test is the test is even not valid if the curvature, the dimension of the indentation is comparable with the indentation of the sphere, because in the Brinell case, because you are too close to penetration, it's no longer valid. Anyway, hardness, it's a local measurement. There is one thing to consider that I didn't tell so far. If you want to have a good stiffness measurement on metals, you need possibly to have, especially for as regard plastic deformation, you see that the big difference is in the Taylor stress and in plastic deformation. Stiffness doesn't change much. But if you perform a tensile test, in order to have results which can be reliable, you need to have 5 samples. In some other materials, you may need many more samples. Steel is quite reliable. You need 5 samples, and you are 99% safe that the average value and the standard deviation of your values might give you some information. And also the standard deviation is small. Still, it's a dream compared with other materials. That's close to the idea. Other materials, you may have a very large standard deviation. Well, I test 5 samples, then I have very large standard deviation. So no value. Your measurement has no value. It's just an indication. But you may need 10, 15, 20 samples. In hardness, you have also the influence of the local characteristics. Here again, steel is quite a dream. You may consider that you have one plate, you make a few measurements on the plate, and it's about repeatable. You have a small standard deviation, etc., etc. But it's a local property. Stiffness is a property that applies to the whole of your sample. Hardness applies to the local, to the point, the local positions, therefore to each point. So you may have variation from point to point. And steel is still good in a good position. With plastics, it becomes much worse, for example. With composites, composite like carbon fiber composites or fiberglass, is much more difficult. Then you have the third characteristic, which I didn't introduce so far, but it is important anyway, is toughness. Toughness is the resistance to cracking. So you have cracks. You may have internal defects like the one we were considering, dislocation and so on, and then you can have cracks. Cracks in steel means that the material will break easily. If you see the crack, the material will break in a few moments. In ceramics is not the case. You may have cracks. If you think of concrete, if you think of a concrete wall, you may have a crack which stays there. Or if you think of a ceramic pot, you may have a crack which was there from your grandmom's time. So a crack may last 20 years and stay still there. It doesn't move. Doesn't develop, and so on. That means that ceramics are tough. And we need that, and we like that for example, for use in buildings, we need a tough material. We need also a material very resistant to tensile stresses, and that's why they make reinforced concrete. In reinforced concrete, you have cement, aggregate, and you have steel bars inside. So I could summarize everything in saying that steel is stiff, diamond is hard. You cannot indent diamond. It's very hard. In fact, you use hard diamond for cutting tips. The diamond saw, cutting tips because the surface, the diamond saw is able to cut, and without being indented, without being harmed or destroyed locally. Hardness is a local. Concrete is tough. Concrete and many ceramics are tough in the sense that you have a crack, which means an obvious defect, a visible defect. You have a crack, but this crack doesn't grow, doesn't develop for many, many years in some cases, and doesn't bring to failure the material. In reality, what happens with concrete is not the problem of cracks. Concrete leads to failure, led to failure, especially in terms of fatigue forces. If the force is always the same, think of the concrete bridges. If the force is always the same, so the bridge withstand its own weight, no cars passing, the cracks can stay there for many, many years. The problem is when the load is variable. So you have a truck passing by, and then the load comes down because the truck has passed. Then you have another truck and another one, and so the load goes up and down. This is fatigue. This phenomenon is called fatigue, and in the end, despite the toughness, the crack goes, and especially you have then chemical attack and so on. You may have some chemicals, for example, by the presence of seawater. You are close to the sea, and you may have some wind, also the wind, which is again is fatigue, and atmospheric fatigue, and in the end you may have seawater and salt and sodium chloride, and other salts which are broken by the atmosphere, and you may have the final break. And fatigue, as I was showing you before, it's a abrupt failure, but an abrupt failure which is shown by the presence of rings on the surface, especially in steel, but also in other structure like concrete, which show that the crack doesn't develop linearly, but it develops by circles, like it is the case for gauge into wood. You can see Okay, I think I said what I wanted to say today. Please start, well, this course, it's more about problems, issues into materials. So think more of the issues than remembering exactly the formula for Brimmer hardness, well, which is useful, but it's more important that you understand the point of measuring hardness, the point of measuring stiffness or toughness, and why a material is applied in that particular situation. Having said that, we see you on Monday at 4. And I would like to say also that all these presentations the slides are available on my web page, on my website. Whilst the recording of the lectures, I put them over the YouTube. I will put also this one later on. And if you look at my name and surname and Fundamentals of Material Science, I am quite sure you should trace them. Please, please send me an email if you have any problems with finding the recordings over the YouTube. But the first three were put over the YouTube, and I checked them with the search engine, and they are there. The system is able to trace. Okay, have a nice weekend, and see you on Monday.